Solving the Schrodinger equation in 1D infinite well. First I will write the Schrodinger equation. Okay. And for infinite well, the potential will be like this. The potential will be equal to 0 between some range between 0 and L, and it will be infinite otherwise. And if you plot the potential, it will be look like this: x versus v. It will be 0 between 0 and L and infinite otherwise. Let's first consider what happens when x is less than 0, which means v goes to infinity. In that case, let's first write down this Schrodinger equation in a more convenient way for studying this condition. Get minus e minus v divided by h bar squared times 2m. That's the wave function. Now, having an energy with infinite amount of magnitude, it's not a reasonable value. Therefore, E minus V is approximately equal to minus V, which means actually minus infinity. Okay, I will write down this equation like this. Let's define this quantity here as lambda squared. When v goes to infinity, lambda also should go to infinity. Now, wave function for this differential equation will be e to the power plus or minus lambda x and some coefficients, let's say prime. Now we are considering x is less than 0. Okay, if we consider wave function as a prime e to the plus lambda x, then when for any value, any small value, since let's consider a small value, whatever small value, we get minus infinity, which means this is equal to 0. So what happens when it is minus lambda? A prime e to the minus infinity times x. This becomes, this everything goes to infinity. It's not a solution. This means when x is less than 0, the solution is, wave function is equal to 0. Physically, that means since the wave function's square or magnitude is squared is equal to the probability of having a particle in that region, there is no any probability of having a particle when x is less than 0. Now what happens? X is greater than L. Again we will get this same wave function, and solutions will be either e to the power plus lambda, I would say proportional to x. Then in this case, since x is greater than L, which means a positive value, we get wave function goes to infinity. It's not feasible. And when we get minus lambda, for any value, this is equal to minus infinity. For x greater than 0, this becomes feasible and it is equal to 0. So the conclusion is when x is greater than L, the wave function is equal to 0. Now what happens? X is equal to 0 and x is equal to L. Then again wave function also get 0 value. Otherwise the wave function is discontinuous. The wave function should be continuous, which means when x is equal to 0, wave function should be equal to 0. When x is equal to L, the wave function again should be equal to 0. Now let's solve for the most important part. of this differential equation. X is greater than 0 and less than L. We have potential is equal to 0. Then the wave function becomes, when we rearrange this, we get this differential form minus 2me over h bar squared square root squared the wave function. I will redefine this term as minus k squared times the wave function. The solutions to this wave function, in general, it will be sine and cosine. A sine kx plus b cosine kx. So you can plug this equation back to this differential equation and verify that it is satisfied by this form. Let's apply the boundary condition we found. When it's x is equal to 0, this part becomes, which means b is equal to 0. When x is equal to L, since b is already 0, we only have a sine kl should be equal to 0. Now, what happens when a is equal to 0? In this case, the whole wave function becomes 0. Which means between minus infinity and plus infinity, there is no any particle at all, which means this is not a feasible solution. When k is equal to 0, again wave function is 0 everywhere. This is also not a feasible solution, which means sine kl should be sine n pi to have a general solution. This gives us kn is equal to n pi divided by L. Alright, our wave function will be k sine n pi over L times x, and here we have our solution for k. Using this, we can calculate energies. Kn is equal to 2m en for nth energy over h bar squared square root, which means nth energy eigenvalue will be n squared pi squared h bar squared over 2ml squared. Here n is any integer, but n is not equal to 0. So hereafter we have only one thing to do, that's determining this a coefficient. That is determined by the normality condition. Wave function should be properly normalized. It is given by this equation. The wave function's magnitude is squared. Integration over minus into plus infinity should be equal to 1. But wave function is equal to 0 when x is less than 0 or x is greater than L, which means this simply was to 0 to L integration. I will plug this s sine n pi x over L here. We have a squared as a constant, sine squared n pi x over L dx is equal to 1. Now, there is a trigonometric identity. Cosine 2 theta is equal to 1 minus 2 sine theta. I am going to use that for this particular equation. Okay, now using this identity, we can rewrite this integration like this. 1 over a squared is equal to integration from 0 to L. We have 1 minus cosine 2n pi x over L dx, we get another coefficient here 1 over 2. So when we integrate 1 from 0 to L, we get just L. From this cosine part, we get some coefficients times sine 2n pi x over L and 0. So this part means actually sine 2n pi minus sine 0, right? So sine 2n pi is 0 for any integer n. So this whole part becomes just 0, which means 1 over a squared is equal to L over 2, which means a is equal to 2 over L square root plus or minus. So we can select either plus or minus sign, because by multiplying wave function by some constant, there's no any physical difference, because we are just considering the wave function magnitude square. That's the physical quantity. So multiplying it by constant doesn't matter. So our final wave function, I will select the plus value, becomes 2 over L square root sine n pi x over L, and n is equal to 1, 2, 3. We can still take minus and minus 2, minus 3 also, but it doesn't affect this wave function, because wave function can be multiplied by any constant without affecting. And I mentioned the any coefficient because we can always normalize, then that coefficient will be gone. And our energies will be energy solutions, or energy eigenvalues will be n squared pi squared h bar squared 2ml squared. The wave function will be 0 when x is less than 0 or x is greater than L. Now I am going to plot few wave functions, actually ground state solution and first excited state solution, in the same potential wave function like this. When n is equal to 1, we have the ground state psi 1, which is equal to 2 over L square root sine pi x over L, and that will be something like this. Its maximum, we get its maximum when x is equal to L over 2. The first excited state will be 2 over L square root sine 2 pi x over L, and that wave function will be look like this. And it has maximums at L over 4 and minimum at 3L over 4. That is, at the maximum point of the ground wave function, there is a node. This is called a node. For bound states, we have nodes for each excited state. So in this case, we have one node when n is equal to 2 nodes, n is equal to 3, like this. Okay, thank you for watching, and I will meet you with another quantum mechanics video.